In the next video, we're going to introduce power-reducing identities. The power-reducing identities take second-degree trig equations and reduce them to first-degree trig equations. So what we're doing is we're taking a second degree, reducing to a first degree, because this is only a cosine of the first, and the same thing all the way through. So these are power-reducing. They're very useful in manipulating trig equations and calculus. So it gives you a good footing of some of the things that you're going to have to do to reduce some of your calculus trig equations to do different derivatives and integrations. So first thing we're going to do is we're going to look at how do we prove the sine squared of theta equals 1 minus cosine of 2 theta. So 1 minus cosine of 2 theta all over 2 has to end up equaling a sine squared of theta. And I'm just going to walk through what they've already done up there, but 1 minus, we're going to have a replacement for our double angle identity for the cosine of theta. And that is equivalent to, and since I want to make it in sine squares of theta, since this has 3 different versions, it's good to pick strategically, and that is make sure you pick your sine one, so minus 2 sine squared of theta divided by 2. Okay, and now we're going to simplify and see if we can get to simplify to sine squared of theta. So we distribute the negative 1, so that's going to become a minus 1, then plus 2 sine squared of theta, all divided by 2. The 1's will cancel, so we got 2 sine squared of theta, all over 2. And those 2's will reduce, and now we're right back to what we'd like to have proven and shown that it's equal to sine squared of theta. So that is a proof or derivation of our power reducing for our sine squared. Now we're going to look at the cosine squared. So we have 1 plus the cosine of 2 theta divided by 2. We want to make sure that this is equivalent to a cosine squared of theta. So again, we're going to start off with our double angle identity here, so 1 plus. This time, since I want it to come back as a cosine squared, I want to pick the identity of that 3 versions that involves just a cosine squared. So it's going to be 1 plus, and then I've got 2 cosine squared of theta minus 1 all over 2. Again, we're trying to see if we can get that to equal cosine squared of theta. And you can see how this quickly reduces. We can get rid of our 1's, and then we've got 2 cosine squared of theta divided by 2, which is just cosine squared of theta, which equals cosine squared of theta, and we've got it checked. Okay, so there's 2 of the 3, and our third one is the tangent squared of theta. We want to prove that 1 minus cosine of 2 theta divided by 1 plus the cosine of 2 theta is really equivalent to tangent squared of theta. So thinking about tangents, tangents are sines over cosine, so in the back of my mind I've got to have a sine over a cosine of whatever our variable is. So we've got options here on our cosine of 2 thetas, and that's how we're going to use those. We want to end up replacing the cosine of 2 theta with a sine version of it. So it's 1 minus, now here comes the replacement. Cosine of 2 theta is equivalent to 1 minus 2 sine squared of theta over, then it's 1 plus, and I want sines over cosines, so in this one I want to replace this double angle with the cosine version of it, which is 2 cosine squared of theta, then minus 1. We want to show that this is going to end up being a tangent squared of theta. So we'll go ahead and run through our negative. So 1 minus 1, then plus 2 sine squared of theta, all over 1 plus 2 cosine squared of theta minus 1. And in the same step, what I'll do is I'll just collect those like terms of 1's. We'll have 2 sine squared of theta all over another 2 cosine squared of theta, which means we can reduce the 2's. We'll have a sine squared over a cosine squared, which is equivalent to a tangent squared of theta. So in this video, what I want to do is present to you the proofs of these double angle, of these power reducing identities by the use of a double angle identity.